Hello. In this video you will see another type of problem you can prove with help of mathematical induction. Let's start. Proving divisibility, problem number 4, and here is its formulation. For each positive natural number n, this expression is divisible by 6 and this expression is divisible by 9. And now you see, of course, that even if we take n equal to 0, so the least natural number, we will still get the true statements, because here we have 0 is divisible by 6, and here also, because 4 to 0 is 1, this will be 0 for n equal to 0, 1 minus 1 is 0, is divisible by 9. But okay, of course, we prove what we are asked to prove, right? So we start with 1. And now I will just write down this proof. And this one I will write down for you after I have recorded this video because of this time constraint. And one more reason is that this particular problem is solved in my course Pre-Calculus 1 Basic Notions. So if it's not enough for you with the written text, which I will deliver, I will do my best to deliver it in a detailed way, then you can watch the solution in the Pre-Calculus course. Okay, so we start. Now, we need to find a way of writing down the induction the thesis. So how can we write down t of n in a more mathematical way? Well, there is a way of writing down that some natural number is divisible by another natural number, and it's in terms of multiplicities. So we can rewrite here this t of n in the way that there exists k, a natural number k, such that n to the third minus n is equal to 6 times k. This is how we can write down in a more mathematical way that n to the third minus n is divisible by 6. So this number is a kind of multiple of 6, and this multiplicity is given by number k. Well, of course, this is also a mathematical way, but this new way is just easier to work with in computations. Okay, but as usually we start by proving the base case. What is the base case? T of 1. How does it look? It looks like this. 6 divides 1 minus 1. It is obviously true because 0 is just equal to 0 times 6. So it is okay. The induction thesis for the base case n equal to 1 is true. Now, let's write the t of n plus 1. What is t of n plus 1? It is that 6 divides n plus 1 to the third minus n plus 1. Right? So we simply take this statement for n and we plug in n plus 1 instead of n. And another way would be, well, the way in which we will work, there exists. And now I can take a number m, which is a natural number, such that n plus 1 to the third minus n plus 1, no, sorry, here is n plus 1, is equal to 6 times m. Okay, and now we have to perform this induction step. We have to show that for all natural positive numbers n, if t of n is true, then it implies that t of n plus 1 is true. So now let's assume that T of n is true for some n belonging to the set of natural positive numbers. And we have to prove, of course, that this means that the thesis T is also true for the next natural number. So this is our induction assumption. And this means there exists a k belonging to natural numbers such that n to the third minus n is equal to 6k. Okay, and now we have to prove that this means that also n plus 1 to the third minus n plus 1 is divisible by 6. So now we have to work with this n plus 1 to the third minus n plus 1. We have to show that this number then is also divisible by 6. And here we have n plus 1 to the third, and you know that you can either perform two parenthesis multiplications like n plus 1 times n plus 1 times n plus 1, and you will get the result. But you can also work with a Pascal's triangle in order to get the coefficients, binomial coefficients for n plus 1 to the third. And how will it look? Well, Pascal's triangle will be 1, 1, 1, 1. If you need an explanation about Pascal triangle, you can have it from this course, Pre-Calculus 2. You got the reference in the introductory video. So here you have the coefficients. They will be 1, 3, 3, and 1. So this means that this first expression here, the cube of this sum, will be n to the third plus 3n squared plus 3n plus 1. Again, instead of this, if it's just seems mysterious, just perform the multiplication of n plus 1 times n plus 1 times n plus 1 according to the regular FOIL rule. Okay, and from this we have to subtract n plus 1. So it will be minus n and minus 1, right? If we skip this parenthesis. And now we see that we have here some cancellation, 1 minus 1. And we know from the induction assumption that T of n is true for our n. So what number is divisible by, wrong pen. What number is divisible by 6? N to the third minus n. You see that we have n to the third here and minus n here. So we can replace this piece by, wrong pen again. We can replace this piece here by 6k. You see what I have done here. Maybe I will write it down here, that I apply here induction assumption. That n to the third minus n is divisible by 6. And now, what about this remaining part? We still have this part here, maybe another color. I will take black for this. And now we still have to prove that this remaining part is divisible by 6. And here I can factor out 3n and write in parentheses n plus 1. So you see that this is my expression, this expression here. Maybe another colored orange would be better. This is my expression for n plus 1 to the third minus n plus 1. And you see that this first part is clearly divisible by 6 by induction assumption. And what about the second part? In the second part we have a factor 3, so this entire term is divisible by 3, and this part is an even number because it's a product of two consecutive numbers. So it means that one of them must be even. One of the numbers 1 of n or n plus 1 must be even. So by this we know that the product is even, and a product of an even number with 3 is divisible by 6. And here you can of course get a thought that this entire problem could easily be solved without induction. And you are right, and keep this thought. This will come back in my next free course about fun math tricks. But now we just see that by the principle of mathematical induction, we have proven that this statement indeed is true for all natural numbers. And this one I will prove simply here in this document, and I will put it on as resources to this video so you can see, and you can of course try to solve this problem on your own. Thank you for watching. Bye bye.